just as they fall here on Earth. In this accelerating rocket, he would experience all
gravity, the maker and the moon
of the cosmos. Program dedicated to Professor C.V. Vishweshraya.
Here is our universe unfolding. The sun with its family of planets, the tailed comets, and stars sprinkled all over. This was pretty much our universe until the dawn of the 20th century. Powerful telescopes of the 20th century improved our vision to include gigantic galaxies and nebulae. Is this all that there is to our universe? Is our universe static and unchanging like what appears to our eyes? Or is this a snapshot of an evolving universe? How are all these entities held together? To seek answers to such deep-rooted questions, we appeal to the same source of inspiration that our ancients drew from: the night sky. Having shone all day, the sun slowly journeys west and sinks below the western horizon. Daylight fades. Dusk envelops. Stars appear, one here and one there. In a short while, everywhere. The bejeweled night sky descends in all its splendor. The imaginative minds of our ancients formed patterns among the distribution of stars. The patterns came to be known as constellations. The entire night sky is divided into 88 constellations. 12 among them, arranged in a narrow belt, are known as the zodiacal constellations. Here you see Scorpius, Virgo, and Leo, to name a few. They serve as the background to describe the motion of planets. Here is planet Jupiter, and this is planet Saturn. Sometimes a planet such as Mars seems to gradually slow down in its orbit. Then it reverses its direction of motion before continuing its onward journey in the sky. This is known as retrograde motion. Various models are put forward in order to account for the observed planetary motions. The model proposed by the ancients to describe the observed peculiar motion of planets was surprisingly complex. In this model, the Earth was the center of evolution.
अबे ऐसा लग रहा है हम लोग घर से
In
नीचे
spite of
गिर
its
रहे हैं।
complexity, this model, a masterpiece
ऐसा
in
लग रहा है हम लोग
geometrical
नीचे गिर रहे
analysis,
हैं।
held sway for nearly 14 centuries among the philosophers in the Western world.
ठीक है।
During the 15th century here in India,
अबे सुन लेना।
Nilakantha Somayaji, a renowned astronomer and mathematician from Kerala, came up with a different model in which 5 of the planets known in his time revolved around the sun, and the whole system revolved around the Earth. Then came Nicolaus Copernicus. He changed what had not been challenged for about measurements of planetary positions made by his mentor Tycho Brahe.
देखो
Kepler clearly demonstrated
वो देखो
that planets actually moved in elliptical orbits. Kepler also established a precise mathematical relation between the period of revolution of a planet
सैटर्न सबसे तेज
and
से घूम रहा है।
its distance
नहीं
from the
मार्स
sun.
सबसे तेज घूम रहा है।
He even imagined physical forces from the sun driving the planets in their orbits. The exact nature of the force came to be understood some half a century later through a piece of
मैं
ingenious
उसकी
work
बात नहीं सुन रहा हूँ, मैं
This
उसको
time-
देख रहा हूँ।
by Isaac Newton.
न्यूटन
A young Newton thought deeply. What pull could hold the moon in
ठीक है,
its
एप्पल
path?
हवा में उड़ रहा है।
Does the force that causes an apple to fall here on Earth extend all the way to the orbit of the
अबे
moon,
देखो गिरा।
causing it to revolve
गोल्डन
around
एप्पल,
the Earth?
the golden capsicum।
These were brilliant, bold, and courageous questions for his time. Newton went on to show that the force really existed in nature and that it diminished with distance. The force came to be known as gravitational force. Significantly, Newton demonstrated that Kepler's laws of planetary motion were a natural consequence of his newly discovered law of gravity.
देखो सबसे तेज।
Here was one universal law that described bodies falling on the surface of the Earth,
कितनी अच्छा है दिख रहा है, ये अच्छा है।
the motion of our moon,
Earth and moon।
the planets and their satellites,
ठीक है,
comets,
वहाँ से आ गए।
and several others.
पापे 16 फेस का नाम कुछ तो डोरेमोन वाले में बताया गया था।
The long-standing geometric universe of the ancients was replaced by Newton's
कोलस है इसका नाम।
mechanical clockwork
पापा इसका नाम कोलस
universe.
है।
Newton successfully applied his newfound law to solve all the major astronomical problems of his time. One long-standing problem that baffled even great minds concerned ocean tides. It is the periodic rise and fall in the levels of large water bodies, peaking 2 times a day. This effect is mostly due to the gravitational force of the moon on the Earth.
अबे नीचे कैसे
Termed as tidal
अबे नीचे
force,
कैसे जा रहा
it
है?
is strong enough to raise ocean levels
नीचे कैसे
into
जा
a
रहा है?
bulge and move it around the
नीचे कैसे
globe
जा रहा है?
as the moon goes around
अबे
the
नीचे
Earth.
कैसे
चांद की वजह से बेटा बोल रहे सुनो ना
The sun's contribution to ocean tide is smaller than that of the moon's. The tidal interaction between a planet and its satellite is not at all
अबे
uncommon.
हमारी तरफ गिर रहा है क्या? ये क्या? ये दोनों कौन है?
The tidal force of planet Jupiter on its satellite Io is so severe
ये मरकरी
that Io's landmass is periodically lifted up by about 100 feet and dropped down as Io orbits Jupiter.
ये क्या
The
रहे?
resulting heat
वो
melts
देखो वो क्या रहे?
sulfur present on Io and it streams out like volcanic lava.
volcanic lava क्या है?
Spectacularly violent tidal interactions can be seen when galaxies approach
Yeah.
one another.
मिल्की भी है।
Tidal force is an inescapable effect of gravity.
पूरा देखा
ये ऊपर हम लोग जा रहे हैं, हम लोग ऊपर जा रहे हैं।
The crowning moment for Newton's gravity came when planet Neptune was discovered.
नेपट्यून और यूरेनस।
Neptune's position was precisely predicted by observing its gravitational effects on planet Uranus.
जिसके पास रिंग है वो यूरेनस है, जो उसके पास रिंग नहीं है
Having glimpsed the effects of gravity on astronomical sizes and distances, let us now temporarily return to the gravity-related phenomena on the Earth.
अरे यार यहाँ पे वेट क्यों? मेरा वेट।
How would objects of different masses accelerate when falling under gravity alone? Here is Brian Cox, noted physicist, simultaneously releasing an iron sphere and a feather. Expectedly, the massive sphere lands first. Now, all the air in the chamber is being removed.
डेंजर।
The experiment is repeated. Now the feather and the massive sphere fall at the same rate at all times. A highly counterintuitive behavior indeed.
ये डार्क।
That is, all falling bodies accelerate at the same rate. The great Galileo had indirectly inferred this profound idea by rolling spheres on an inclined plane. Gravity has had a profound effect on the lives and works of great minds as Galileo, Kepler, Newton, and so on. What about the effect of all-pervading gravity on life itself? The thin blanket of atmosphere hanging by gravity's thread offers the foremost protection from the harmful radiations coming from space. Pieces of rock from space hurtling towards the Earth mostly burn up in the atmosphere before they reach the ground and cause damage to living beings. Primitive or complex, small or big, terrestrial or aquatic, plant or animal, all forms of life are affected by gravity.
all the
The shoot and the root of a germinating seed grow and develop in different directions in response to gravity in order to carry out their respective functions. Seeds that disperse by wind have to dilute the effects of gravity to stay afloat in air for a long time, long enough to be carried far away from one another. This is essential to avoid competition for natural resources such as light and soil nutrients. And how well they achieve this.
वो बीटल है।
The tiny fungus here shoots spores
चूहा।
that moved faster than a bullet fired from a shotgun. Yes, faster than a bullet.
वो गोली थी.
The speed and the manner of our walking or running is also influenced by gravity. On the moon, under reduced gravity, it is difficult to walk at speeds like we do so on Earth. So astronauts on the moon find hopping to be easier than walking. In the evolving story of gravity, celestial motion once again plays a pivotal role.
अब चुप हो जाओ ना.
It was observed that the orbit of planet Mercury did not close on itself. Also, the farthest point in its orbit around the Sun gets gently shifted at the end of each revolution. Taking into account the effects of all the massive bodies in the solar system, Newton's law almost fully accounted for the observed shift.
3 बार का
Almost,
चक्कर हो गया. हम लोग क्यों
but
हिल रहे हैं?
not fully.
अबे हम लोग हिल रहे थे ना.
Newton's gravity that had remained unchanged for 2.5 centuries was due for a revolutionary change to explain this discrepancy. We shall take a look at the new idea of gravity and how it completely explained the anomaly observed in Mercury's orbit. The seed for this new idea was sown in the year 1907 when Albert Einstein came to this profound realization. The happiest thought of his life, that a person falling freely experiences weightlessness. Well, if some of you are wondering if this is the surest way to lose one's weight, please hold on. Conditions apply. You will regain all of it once you land. On a serious note, the way to realize Einstein's happiest thought is to be adventuresome. Jumping off the cliff, safely of course, is one of the ways. Zooming down a steep slope in a roller coaster is another. By going into a free fall. If the effects of gravity can be nullified, can they be created too? Yes, they can be. And here is one way to do it. Consider an astronaut inside a rocket in space. Objects dropped by him don't seem to fall, just as in a space station. As the rocket is accelerated, he would actually tell you that the objects fell to the floor just as they fall here on Earth. In this accelerating rocket, he would experience all the effects of gravity, including weight. That is, acceleration is equivalent to gravitation. This is the central idea on which Einstein built his new theory of gravitation, known as the general theory of relativity. According to it, gravity is not a force, but one that curves space-time, a notion impossible to even imagine, and one that does not and cannot exist in Newton's framework of gravitation. Since all of us are not geniuses like Einstein was, perhaps an analogy is in order here, even if it is a crude one. The stretched acrobat net here represents space-time. It is flat when there is no mass on it. Objects travel straight along expected lines. Next, the acrobat lands on the net. The net is vastly curved around him, and far away from him, it still remains nearly flat. Analogously, gravity, a fundamental property of mass, curves space-time. The curvature dictates the paths of light and of objects. It is now time to recall the problem of planet Mercury's orbit. Planet Mercury does not return to the same position after completing one revolution. This is due to the space-time curved by the Sun's gravity. Thus, Einstein's new theory precisely accounted for Mercury's orbit's anomaly. Next, Einstein predicted a phenomenon that had never been observed before. That light traveling along space-time, curved by a star, would bend instead of traveling straight. A group of scientists set out to verify this during a total solar eclipse on May 29th, 1919. The moon's shadow races across the earth. It's about 2 p.m. local time in the island of Principe, West Africa. The dazzling sun is gradually eclipsed by the moon. The untimely appearance of stars provides a surrealistic feel.
Black hole.
A team of astronomers photographed the starry sky around the sun. It was then compared with photographs of the same part of the sky taken a few months before and after the eclipse. The apparent shift in the positions of stars clearly indicated bending of starlight, as predicted by Einstein's theory. It is always delightful when a great and beautiful idea proves to be consonant with reality, isn't it? The theory was rightfully hailed as one that ranked among the greatest achievements of human thought. The subtle phenomenon of light bending manifests in a more dramatic manner when light from distant sources pass by clusters of galaxies that are billions and trillions of times more massive than the Sun. Now, guided by a substantially curved space-time, light takes two or more paths in reaching us, leading to multiple images of the same object. The effect is aptly known as gravitational lensing. Space-time not only bends light but stretches light waves as they propagate from a region of high space-time curvature to a smaller one. This is known as gravitational redshift. Space-time curvature profoundly affects time too. Time ticks faster where the space-time is flat. Steeper the curvature, slower does a clock run. Can the space-time curvature ever get so steep that time nearly comes to a standstill? Even though Einstein was unsure of its reality, his theory predicted the possibility of an esoteric entity that could almost freeze time for a distant observer. It is a black hole. A black hole takes birth in the death throes of a massive star. A long time after a star is born, there comes a time when temperature in the core is insufficient to sustain nuclear reactions. Now, gravity crunches the core, thereby increasing the temperature. This temporarily reboots the nuclear reactions in the core. Meanwhile, the outer envelope of the star expands. After some time, nuclear reactions once again come to a halt. In a significant piece of work, celebrated astrophysicist Professor S. Chandrasekhar first showed that under such circumstances, gravitational collapse is inevitable. Now the mass of the core decides the final resting stage of a star. If the mass is less than 1.44 times the mass of the Sun, known as the Chandrasekhar limit, it ends up as a white dwarf. If it is more than that, but less than about 2.5 solar masses, it undergoes a series of convulsive contractions, ultimately yielding to gravity in a gigantic implosion, causing a supernova.
ये क्या हुआ? पापा सन फूट गया.
The ejected matter contains a rich diversity of chemical elements, most of which are created in less than 1/10 of a second.
Carbon, fluorine,
Without some of these,
phosphorus,
it is impossible to think of life as we know it here.
iron.
Life in all its form is
किधर है बंदा?
the gift
ये
of
गिरा.
gravity.
ये क्या है? ये क्या है?
अच्छी है, अच्छी है.
What used to be the stellar core is now a super dense mass of neutrons, a neutron star. A neutron star cannot be more than 3 solar masses. If the mass of the stellar center exceeds 3 solar masses, then no known force in nature can stop complete gravitational collapse. The result? Gravity's most enigmatic manifestation, an invisible entity called a black hole. Gravity turns out to be the great dictator at every stage of stellar birth, maturity, and death, playing the role of generator, operator, as well as destroyer. If a black hole is invisible, how does one detect it? A black hole produces fantastic, distorted, multiple images of distant stars and galaxies due to gravitational lensing. Gravitational redshift is another way of detecting them. Light reaching us from a star approaching a black hole appears reddish. These unimaginable effects on light reveal a black hole lurking in the depths of space. And it's no wonder that while Einstein's theory predicted the possibility, he strongly suspected their existence. A black hole can also be detected by its gravitational effects on matter in its vicinity. Here you see a black hole drawing in and spreading up matter from a neighboring red giant star.
स्पेस में सारे
It is the tidal effect on a grand scale.
पापा
Rain falling matter heats up, emitting X-ray jets.
अगर हम लोग लेने की कोशिश करेंगे तो क्या होगा?
नहीं ले.
Space-based X-ray telescopes such as ISRO's ASTROSAT and NASA's Chandra telescope detect such jets and thereby indirectly establishing the black holes associated with them. Nearby black holes mutually exert gravitational effects on one another. One such interaction made big news in 2015. Here we reconstruct the event in a minute of what actually took thousands of years in real time. Black holes revolving around one another continuously lose energy, drawing them closer to one another. The black holes revolve with increasing speed as they are drawn closer and closer. Finally, they merge into one single black hole, whose mass is less than the mass of the two black holes put together. All the energy and mass lost by them appears as gravitational waves, precisely following the principles of Einstein's theory of gravitation. The gravitational waves hardly interact with anything. It took two gigantic super-sensitive detectors, one at Livingston and the other at Hanford in the United States, to detect them for the first time. Gravitational waves were so weak that they displaced the detectors by less than the size of the nucleus of an atom. The direct detection established for the first time the reality of both gravitational waves and black holes, both doubted by Einstein. It is a matter of great pride that the discovery team included several scientists from Indian research
ये
institutions.
वाले तो हमारी जगह पे थे.
Early work on black holes in the 1970s by the founding director of Jawaharlal Nehru Planetarium Bengaluru, Professor C.V. Vishveshwara, popularly known as the Black Hole Man of India, and Professor Bala Ayan, another great general relativist and closely associated with all the activities of this planetarium, have played a key role in gravitational wave research. Since the first detection, several gravitational wave events have been detected. The merger of two neutron stars being a notable one.
अबे ये तो blast हुए.
In the coming years, gravitational waves will certainly present the universe in a new light. With no knowledge of gravity, Ptolemy created a geocentric, geometric universe that lasted for 14 centuries. Based on his theory of gravitation, Isaac Newton created a mechanical clockwork universe that lasted for 3 centuries. The space-time curved universe, born out of Einstein's sheer genius, has completed a century. Let us enjoy the fruits of the present one, until this makes way for a new or a modified idea about gravitation.
खत्म.